Okay, friends, we're almost done. Pretty much last week. Everything's cool. So let's just pick up where we left off. Last time we looked at this. We looked at how to go from a hydronium ion concentration to predict what the pH was. And pH is a scale that goes from approximately -1 to 15, although it can go a little less than -1 and a little more than 15. And those pHs correspond to a concentration of hydronium ions. And hydronium ions are what happens to water when water accepts a proton. And water accepts a proton when water is exposed to an acid. So, what we did is we used this. pH is equal to the opposite of the log of the hydronium ion concentration. And then we did it like this, and we said, well, if we had 0.25 molar hydrochloric acid, and hydrochloric acid is a strong acid, meaning that it fully reacts with water. If we had that, then we would have 0.25 molar hydronium. And if we had 0.25 molar hydronium, the opposite of the log of 0.25 is 6/10. So the pH is 6/10. But to tell you the truth, this isn't all that useful in the lab because you normally know what the concentration of your acid is because it's normally labeled, unless some funny stuff's going on. And oftentimes funny stuff is going on in the lab. So that's what we're here to talk about today. We're here to talk about how to go from a pH to a hydronium ion concentration. So this is sort of detective work that you will be doing in the lab a bunch, especially in biotechnology next year. You might do this some. So anyway, let's say we had some unknown concentration of a strong acid, nitric acid in this case. Remember nitrate, itis, ate, ick, nitrate, nitric acid. Oh, nitric acid. And we don't know what the concentration of it is. Well, what we can do is we can get some and pour it into a beaker, and then we can use a pH probe to see what the pH is. In real life, you would never take straight nitric acid and put a pH probe in it because you damage the pH probe. So in real life, what you would do is you'd take a little bit of the acid and add it to a lot of water to make a dilution. And then you'd have to account for the dilution in your final calculation. But we're not going to do that right here. We're just going to say that this is a magic pH probe that won't get damaged by this nitric acid. So let's say we take this pH probe and we measure the concentration of this nitric acid. And let's say that the pH comes out to be, oh, I don't know, let's say it's pretty darn acidic. Let's say it comes out to be 7/10. Does that sound good? So how can we use this pH in order to determine or infer the concentration of this nitric acid right here? So here's the formula we used last time. pH is equal to the opposite of the log of the hydronium ion concentration. If we do algebra to solve to get hydronium ion concentration all by itself, this is what we'd end up with. Don't ask me why, because I don't know. We'd end up with this. The hydronium ion concentration is equal to 10 to the opposite, 10 to the power of the opposite of the pH, 10 to the negative pH power. Power. Yeah? So let's do it. Wanna? I wanna. Fine. So the pH was 7/10. So that means that the hydronium ion concentration of this acid is equal to 10 to the negative 7/10 power. So last time I asked you guys to download this Desmos app for your phone because you might not have a scientific calculator at home. It's not as nice as the scientific calculators we have at school, but it's going to work for us. So here's this Desmos app right here. So how do I do 10 to the negative 7/10 power? I start on the main menu right here. Let me zoom in on this sucker. Yeah. Start on the main menu right there, and then I'm just going to type in 10, and then I'm going to switch to the function menu up here, function menu, dink, like that. And then I'm going to use this exponent thing here, this a to the b power right here. So I'm going to click that right there, and then I need to make it to the negative 7/10 power. So I'm going to go back to the main menu right here, boom, and I'm going to say negative 0.7, negative 7/10. And there's my answer right there. What do you guys think about that? The answer is, go back here. The answer is that the hydronium ion concentration is equal to 0.1995. So sometimes there's going to be a bunch of zeros over here, a bunch of zeros over there. So a lot of times we'll like to report the answer in scientific notation. So in order to do that, the decimal place needs to be between the 1 and the 10th place right here. So to do it in scientific notation, I would say that the hydronium ion concentration is equal to 1.995 times 10. So is this number bigger or smaller than the real number? This is the real number, and this number is bigger than the real number. How much bigger? 1 order of magnitude, 1 order of magnitude. So that would be times 10 to the 1. But it's not bigger, it's smaller, so it's going to be times 10 to the negative 1. Yeah. Okay. Well, we know from previous studies that we did that the concentration of hydronium in a strong acid is equal to the concentration of the strong acid itself. Therefore, the concentration of this nitric acid right here, so the concentration of nitric acid is equal to the concentration of hydronium, which is equal to 1.995 times 10 to the negative 1 molar. Yeah, that's molar right there. Whoops. Yeah, that's molar right there. Yeah. Yeah? 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 Sounds super confusing, but it's actually kindergarten. All you got to do is take 10 and put it to the negative pH power. The hard part is learning how to do that on your calculator, but I just showed you guys so you can practice and get super buff at it. Okay, what do we got? Tuesday? We're almost done. It's already Tuesday. TGIT. TGIT.